drag. Let's go. Drag. So, welcome again to the drag video. So, yeah, let's talk a little bit more about the drag force. What is the drag force? This is a force that opposes motion as it moves through a fluid. Okay, this is a force that opposes motion as it moves through a fluid. Okay, so when do objects, so a fluid, basically fluids encompass air or water, all right? So gases or water. A fluid is, just want to get that clear. I'm gonna just move these a little bit. I left my eye. Okay. Sure, whatever. I'm not even gonna trip. All right. So, when do objects experience drag? So objects experience drag running. Or even walking to an extent, they experience drag. Swimmers when they dive, or even when they are swimming, not only when they dive. So really, a way to describe drag. So let's see, drag is the feeling of resistance by a fluid on an object. All right? That feeling of resistance. So when you put your car, so when you're driving on the highway and you have your hand out the window, you feel that air just trying to push your hand back. That's a drag. All right? So that feeling of drag. All right? Now, what's the magnitude of drag? All right? Ft is going to be equal to 1/2 c rho, another Greek symbol, a v squared. All right? What's A? A is the cross-sectional area. I'll get into that, don't worry. C is the drag coefficient, another coefficient. Then we have rho, which is the density of the fluid. And then v squared is the velocity the fluid is moving at. All right? So now, important to note, drag is a function of velocity. All right? So basically, this is the relationship. Drag is directly proportional to velocity squared. So this is what, if we were to track drag over time over a bunch of velocities, it would be a quadratic. And this would just be a regular V, not Oopsie. Okay, it would just be a regular V. So drag is proportional to velocity squared. So then, what's C? Let's talk more about the drag coefficient. Yeah, drag coefficient. And sometimes you see drag referred to as just D. Like D is fine. It's the same thing. So sometimes the force of D depends on who you meet. All right, it's fine. So the drag coefficient. So one thing about it, the coefficients, why we like them, they are determined experimentally. All right, they're determined experimentally. Different objects have different drag coefficients. All right, different objects have different drag coefficients. Drag coefficients. So now, what is it though? What is it? Well, let me just kind of just go up a little bit. The drag coefficient is basically a measure of how aerodynamic an object is. All right. So I like to think about it as an aerodynamic score. All right. In fact, aerodynamic score basically. All right. How fast does it go to air? It factors in the shape of an object, the shape of an object, the roughness of its surface, and the velocity of its moving at. Right? You have different drag coefficients at different velocities to some extent. So basically, let's say different objects have different drag coefficients. So, an example, if we have a Toyota Camry of a drag coefficient of 0.28, this is pretty decent. All right, a Formula One car. There's a lot of research done to make Formula One cars just as efficient as possible. All right, so these have a very high drag coefficient, and that's ranges between 0.7 or 1.1. So normally the higher your drag coefficient is, the more aerodynamic your car is. All right, it doesn't necessarily mean that you have less drag as possible. No, it does not mean that. It just means that your shapes are pretty efficient and kind of just make you move through the air or whatever surfaces you're encountering a lot faster, a lot better. Listen, a bicycle has a coefficient of 0.9, all right? And so on and so forth. There are many objects, and we can go on forever talking about drag coefficients. All right. So, what's A? A is the surface area. A is the surface area. All right. So the surface area of an object. That's so if I have an object falling, all right. Remember our formula is FD is equal to 1/2 C rho, so I need to see it, V squared, yeah, oops, rho V squared times A, oopsie daisy, let me get this right. So A is basically the surface area, the cross-sectional area. Now what do I mean by cross-section? All right, so if I have a sphere, drop, this is a circle, but let's say if I have a sphere, yeah, and I cut the sphere in half, I will see a circle, a plain old circle, and that the cross-sectional area of a circle is going to be pi r squared. So our drag kind of considers the cross-sectional area of an object. The force of drag, the magnitude of drag, considers the cross-sectional area of an object. What about if I'm dropping a cylinder? All right. Let me get if I'm dropping it in this angle. I hope it's on. All right. If I cut it in half, again, this will be another circle. That's more of an ellipse, but you know what I mean. What if I'm dropping my cylinder on its side? And I cut it in half. What shape do I have? I got a rectangle. Alright? And the area of a rectangle is the length times the breadth. Well, this here would be the diameter of this circle. So diameter times, let's say if my length is referred to as h, so I say h, and or if you want, say, like your book says, the diameter is just 2 times the radius, so 2r, and cause the length L, cause the length L, and the area will be, the cross-sectional area will be 2L. So yeah. Then, so let's see, where is drag applied in the real world? All right, so we have, Formula One. All right, Formula One engineers invest a lot of time. Swimsuits are now pretty tight on the body to minimize drag. Swimmers also cut their hair just to reduce drag, and so do runners as well. Runners wear full body suits which are tight to reduce tight on the skin or to reduce drag so they can run faster or swim faster or whatever. Yeah. All right. Terminal velocity. Let's get to it. Okay. Let's analyze a skydiver. Yeah? A skydiver is falling. Let's see its free body diagram. You have the weight. Of course, we have the weight. Now, what we've just learned today is that if an object is falling through a fluid, whether it's air or whether it's air or whether it's water. Oh my God. It experiences drag. So, how should we think about this? Well, okay. Yes, we do have an equilibrium, but it's more interesting than that. It's a lot more interesting than that. So, let's see. The skydiver will be falling. Yes, we all know that. But as he's falling, he is accelerating. All right, we know he's accelerating, 9.8. But the real question comes in: how long will he accelerate for? Or at least till when will he accelerate? Well, so as we know, acceleration is the change of velocity. So he will accelerate until his velocity allows his drag to match his weight. All right, so we know the formula for drag is 1/2 c rho a v squared. So the skydiver will accelerate until f of d is equal to equals to our force weight, so equals to our weight, and we call the velocity at which the the drag force is equal to the weight force, the terminal velocity. All right? So let's see. Terminal velocity is when our drag force is more than our weight force. All right? Dope. Okay. How do we find the formula of terminal velocity? Okay, so we need the same things we've been doing. So we have our drag. We have our weight. Imagine that a straight line, not to be crooked, I apologize. So we know that, well, I'm going to ignore the x direction. So this is, let's say the sum of forces in the y direction going to be equal to FD minus omega. Yeah? Agreed? Yeah, because I'm positive in the with the drag and negative with the weight. And because I'm at terminal velocity, you remember our skydiver this is our skydiver, it's only going to accelerate until I reach terminal velocity. I know in the y direction I'm not accelerating, so f of d in my vector forms is going to be equal to 0. All right? And then now I get my f of d is going to be equal to weight. Now, what's the magnitude? Let's get it to a magnitude form now. All right, the magnitude form of f of d is 1/2 c rho v squared. All right, and the magnitude form of that is mg. All right, mg became positive. Yeah, mg is positive. mg is positive right now. So now we can solve for v, and then what we get, let's see, if I get v squared is going to be equal to, say, multiplied by 2 mg divided by c and rho, and then I can square root both sides. I get 2 mg squared, drag coefficient, times rho. And that right there is my terminal velocity. All right? That right there is my terminal velocity. The formula for terminal velocity is over here. I forgot my area. Oh my God. Area. All right. Area. Okay, I apologize. So yeah. So let's think about this formula. Yeah, let's think about it. It's very interesting. So what I'm saying is, look, imagine, so let's about formula, yeah? We got V is equal to 2 mg c rho times A. So our cross-sectional area, imagine I have a very wide paper. So the wider I am in the air, like the wider my surface area is, the larger my surface area is, the smaller my terminal velocity will be. But the larger my mass is, the larger my mass is, the larger my terminal velocity will be. And by the way, when the skydiver falls down, he falls down moving towards his terminal velocity. So if you have a small surface area, but a large mass, your terminal velocity will be higher. Yeah? If you have a large surface area and small mass, you will have a low terminal velocity. All right, and of course, if you have what am I writing? A low. Can you cancel that? All right. Terminal velocity. A large surface area and a small mass. All right. You have a low terminal velocity. So I'll say V terminal will be very low. All right. So, and of course, if you have a small surface area and the small mass, you'll be very low. So basically what I'm trying to say here is that larger objects with a larger mass will fall faster. And if you fall faster, the impact on the ground will be a lot harder on your body. But if you're a small object with a small mass, there's even a chance you may survive falls from the highest of areas. All right? So, yeah, anyway, that's all for today. I hope you enjoyed this video. And, yeah.